I'm going to talk about Glivenko classes and constructive cut elimination in infinitary logic. So this is the outline of the talk. First, we introduce infinitary logics and the calculi that we are using. Then I'm going to introduce the main tool, which are embeddable derivations that we will use during the proofs. Then I will show some results that structural rules hold, and we show a constructive proof of cut elimination. And in the end, we show some Glivenko style results for infinitary logic. Okay. So first, let me introduce the syntax. We have atomic formula, which we denote by P usually. Then we have countably many predicates and function symbols and equality. Formulae are built up using, in addition to the standard connectives and quantifiers, also countable disjunctions and countable conjunctions. Of course, the language is not minimal, since we can define finite conjunction and disjunction as special cases of the infinite ones, but we prefer to have all of them as primitive. Okay. So sequence, as usual, are expressions of the form gamma rho delta, where gamma and delta are finite multisets of formulae. And these are the rules that we have for infinite disjunction. So we have an infinite collection of right rules, one for each formula, for each natural number. So one for each formula in the disjunction. Okay. While we have a single rule, a single left rule, but which has countably many premises. Again, one for each natural number or for each formula in the disjunction. So derivation built using this rule are in general infinite trees that can have countable branching, but each branch has a finite length. So the leaves of the trees are sequence where gamma contains a bottom, or gamma and bottom as gamma and delta have an atomic formula in common. Okay, so this is the classical calculus. So the rules for infinite conjunctions are just the dual of the ones for disjunction, and the other rules are the usual ones. Okay. Then we can have we have intuitionistic calculus. So the intuitionistic infinitary calculus G3I omega is obtained from the classical one by replacing the rules. So the rules for implication and universal quantifier are the usual ones. And we also replace the right rule for infinitary conjunction by removing the context on the right-hand side here. So we do the same as we do for the right universal. And then we have the minimal, the calculus for minimal logic, which is obtained from the one from intuitionistic logic by replacing the left rule for bottom by this initial sequence that has bottom both on the left and on the right-hand side. Okay. So then we can have some extensions with the rules for geometric theories. So we know that in finitary logic, if we add geometric theory, if we have geometric theories, so if we add the geometric axioms, what we get maintains the structural properties of the ground sequence calculus. So we can generalize this to infinitary geometric logic. And we can consider infinitary geometric theories, which are axiomatized by geometric implications, which are sentences of this form. So the universal closure of C implies D where C is a finite conjunction of atomic formulae, and D is a finite or countably infinite disjunction of expressions of this form. Okay, so such a sentence can be expressed as a rule this way. Okay, so we have some examples. For instance, the axiom of torsion abelian groups, which is this one, can be expressed this way as a rule. The axiom for Archimedean ordered fields, the axioms of connected graphs, and also the definition of transitive closure, which is this one, can be expressed as these two geometric rules. Okay. The cut elimination procedure that is given in the work by Dikov and Negri from 2014 and the work by Negri from this year is non-constructive. This is a typical limitation of cut elimination in infinitary logic, since the proof uses the commutative sum of ordinals. Natural sum is inescapable for proofs using the cut height as an inductive parameter, and it makes proof non-constructive since its definition utilizes the Cantor normal form of ordinals to base omega. This normal form is not available in constructive Zermelo-Frankel set theory or intuitionistic Zermelo-Frankel, and thus we need a different approach. So we choose this approach that uses embeddable derivations. So what are embeddable derivations? We inductively define two relations, which we call embeddable and strictly embeddable. This one, okay. So by these four clauses, if D and D prime are initial or empty sequence, then one is embeddable in the other. If we have two derivations this way, and for each branch of the first derivation, there is a branch of the second derivation into which the first is embeddable, then the first derivation is embeddable in the second derivation. If we have a derivation D embeddable in a derivation D prime, and we have that D prime is a branch of D double prime, then D is strictly embeddable in D double prime. And in the end, we want that if D is strictly embeddable in D prime, then D is also embeddable in D prime. Okay, so a couple of observations. Embeddability is a non-strict preorder, while strict embeddability is a strict preorder. So given a calculus G, we denote this way the fact that there is a derivation D of sequent gamma arrow delta in the calculus G. We say that a rule is proof embeddable admissible or PE admissible if for each derivation D of the top sequent there is a derivation D prime of the bottom sequent such that the derivation of the bottom sequent is embeddable in the derivation of the top sequent. We can prove results of P substitution admissibility invertibility similar to those of height-preserving substitution admissibility invertibility. So this includes substitution. So substitution is P admissible. Also, the rules of weakening are P admissible in all three calculi that we are considering, the classical, the intuitionistic, and the minimal one. Invertibility, so in the classical calculus, each rule is P invertible. In the intuitionistic and minimal calculi, all rules except for the right rule for implication, the right rule for universal quantifier, and the right rule for infinite conjunction is P invertible. the rules for contraction are be admissible in all calculi. Okay, so these were the rules. What is missing is cut. So this requires a longer proof. So first, we have to define what is a cut substitutive rule. So a rule is cut substitutive if each instance of cut with the cut formula, not principal, in the last rule instance rule of one of the premises of cut can be permuted upwards with respect to rule. Okay, so we have two lemmata. So each rule of the classical calculus is cut substitutive, and each rule except the usual three ones in the intuitionistic calculus is cut substitutive. Okay, so we can prove this lemma of right reduction if we are in G3 or either the classical or the intuitionistic calculus and all the following hold. So if there is a derivation D1 of the sequent gamma arrow delta comma A, if there is a derivation D2 of A comma pi arrow sigma, if A is principal in the last rule instance applied in D1, if A is either an existential formula or an infinite disjunction, then A is not principal in the last rule instance applied in D2. So if all this for old, then there is a derivation in the calculus that we are considering, concluding pi comma gamma arrow delta comma sigma. So we cut the formula A from these two, okay, containing only cuts on proper subformulae of A. So the proof is well-founded, is done by well-founded induction with strict proof embeddability in the derivation D2 of A comma pi arrow sigma. Okay, so a similar result can be done for left reduction. So, okay. Now, in order to prove cut elimination in a constructive way, we use bar induction as it is done in insiders for omega arithmetic. And this strategy allows us to completely avoid the use of ordinal numbers. So what is bar induction? If we have two unary predicates, B and I, where B is called the base predicate and I the inductive predicate, a finite list of natural numbers. We denote the list by alpha, beta, and so on. So if we have these four conditions that are B is decidable, every choice sequence has a finite prefix satisfying B, B of alpha implies I of alpha for every finite list alpha, if I of alpha succeeded by n also for all natural numbers n, then I of alpha also. So if all this for old, then I also for the empty list of natural numbers. Okay. So we use this to prove cut elimination, which is that cut is admissible in this calculus. So we use bar induction in two stages. First stage. So to show that an uppermost instance of cut on a formula A occurring in D is admissible. So we represent formulae through their formation tree, and we use natural numbers to encode the nodes of the tree and lists of natural numbers to encode the branches. So we have to say what B and I are. So the base the base predicate is that alpha encodes a branch whose last element is an atom or bottom. And the inductive predicate is that alpha encodes a partial branch whose last element is the code of a formula B, such that an uppermost cut on B is admissible in the calculus. And we have that all the hypotheses of Bar induction are satisfied. Okay, so, and we use the left reduction to prove the clause 4. Okay, by Bar induction, so we can apply Bar induction, and we conclude that the cut on A is admissible in this calculus. Okay, so now we again use Bar induction to show that all cuts can be eliminated from D. So we consider a derivation D in the calculus plus cut, and we use natural numbers to encode the premises of rules and lists of natural numbers to encode branches of D. So in this case, the base predicate is that alpha encodes a branch ending in a leaf, and the inductive predicate says that alpha encodes a partial branch in the derivation whose last element has a cut-free derivation. Okay, so also in this case, we satisfy all the clauses of Bar induction. So we can apply Bar induction and conclude that the conclusion of D has a cut-free derivation. Okay. So we have that all structural, we have proven that all structural rules, including cut, hold in our calculi, include, and we did this constructively. Okay. Now we pass to the last part, which are Glivenko style results. So what is Glivenko's theorem? Glivenko's theorem states that a negated propositional formula provable in classical logic is also provable intuitionistically. Glivenko style results in general are results about classes of formulae for which classical provability implies intuitionistic probability. Okay, so why are these important? So it may be easier to prove theorems by classical logic rather than intuitionistic logic, while a proof in intuitionistic logic can be associated to a lambda term and thus obtains a computational meaning. There is a wide conceptual umbrella concerned with the computational content of classical theories, and we can have a shift of perspective in foundations. So rather than developing constructive mathematics separately, as in Brouwer's program, one can study which parts of classical mathematics can be directly translated into constructive terms. Okay, so we generalize the results by Sara Negri, which are the simplifications of Orevkov's result using G3 sequence calculi to the infinitary setting. So we consider these 7 sequence classes. So this means that the sequence have no positive occurrence of this certain connective or quantifiers, and the minus as an upper index means that it has no negative occurrence of that connective or quantifier. N means that this implication is not a negation, and SC refers to the class of single succedent sequence. Okay, so if we consider the first class, what we get is actually Barre's theorem for infinitary logic. So if we have a sequent gamma arrow delta in the first class, and we have a derivation D of such sequence in the classical calculus, then we have a derivation d prime of that same sequence in the intuitionistic calculus, such that the intuitionistic derivation is embeddable in the classical derivation. If moreover, there is no negative occurrence of falsity in that sequence, then d prime is a derivation in minimal logic. Okay. Now let G3 CIM dot H omega denote extensions of the calculus by single premise geometric rules. We get these two. We can group the results about the remaining classes into theorems. So if we have a sequence in Ci prime where I is either 2, 4, 5, or 6, so in one of these 4 classes, and we have a derivation D of that sequence in classical calculus, then we have a derivation D prime of that sequence in intuitionistic calculus, which is embeddable in D. And moreover, as before, if there is no negative occurrence of bottom, then that derivation is in minimal logic. If we consider the remaining classes, which are 3 and 7, we get a similar result. However, what we don't get is that the derivation is embeddable in the intuitionistic derivation may not be embeddable in the classical one. Okay. So to conclude, we have an optimality conjecture. So by analogy to the Infinitary case, we conjecture that if for a class of sequence Infinitary classical derivability yields Infinitary intuitionistic derivability, then the class is contained in one of the seven classes Ci prime, where I is from 1 to 7, so the 7 classes that we have here. Okay, so I conclude. Thank you for your attention.